Ladies and gentlemen, hello from my side. I'm speaking on behalf of my colleagues from the Code ADC team about the latest developments of our MJAX solution. I will start with a short status update. Then I would like to talk about planned model changes and the importance of satellite metadata availability for these changes, and I would also say some words about empirical solar radiation pressure modeling for the orbit normal mode, and conclude my talk with a summary and outlook. We spent some time since the last IGS workshop with a survey on our products and the status achieved so far, and also about the weaknesses of our solution. We published this in a paper which can be used as a reference for our MJAX product. Moreover, we were busy with operational tasks, for example, adaptation to the long-run X3 file names, switch to the IGS 14, and also change to the default untext file provided by the IGS since autumn of 2016 with all satellite systems included. And from a content point of view, it meant that we changed to estimated Galileo values provided by Peter Steigenberger. Yes, and most important was probably, but not visible to outside, that we integrated our MJAX solution now fully into our standard IGS routine. So we merged software, we merged configuration, we merged metadata files, and it's now coming from all of us and everybody. Every member of the AC team is now overseeing also the MJAX solution, and this enables also parallel developments. If we look at some results, we can, for example, see the clock corrections, and as one quality measure, we can see how linear these clocks are. By computing a linear clock fit, and we see that many satellite clocks are very good, which are in the orbit currently. So we see there are many very good GPS clocks, and also the Galileo maser clocks, of course, and also the QZSS clock. So here, for example, small median and interquartile range indicates a good clock. If we look at the orbits, we can validate them with SLR residuals. There we see that especially for Galileo and QZSS, there are still very large offsets, and they indicate that we have some severe modeling problems, deficiencies in our orbit determination, which have impact on the radial orbit component or the orbit scale, and most likely they are related to missing albedo and antenna thrust modeling or insufficient antenna calibrations. So we would, or we plan some significant model updates related to these issues. For Galileo and QZSS, we would like to add albedo and antenna thrust modeling, and we would also like to activate the attitude model for Galileo. We would like to activate pulses like we do already for GPS and GLONASS. And yes, we also have to think about the antenna model. Discussion will be provided by my colleague Arturo Filiger in plenary session 6. Yes, so far some of these model implementations were difficult because of missing metadata, but the situation improved, at least for Galileo, since the end of last year, when the GSA published metadata of the Galileo IOV satellites. But there are many, still many unknown information also about other satellite systems, but also still about the Galileo satellites. And there we have to make some assumptions. So for example, for Galileo, we could use the disclosed IOV metadata to build a very simple box wing model. We can use the disclosed attitude model. We could assume the same properties for FOC satellites, but we know that it's not true. So the question is, shall we do it or not? Meanwhile, the DLR has provided measurements for the transmit power, so we can use them. And for QZSS, we have very little information about the size and mass of the satellite, but the transmit power was published. So if we use our current solution as a starting point, called operational solution, we have very large SLR offsets. If we now add the albedo model, then we can reduce the antenna, we can reduce the SLR offset. And for QZSS, in the first experiment, we have assumed probably too light satellite mass. Then we add antenna thrust. So for Galileo, we had 3 different antenna thrusts tested. The one which was proposed for FOC satellites, for IOV satellites, and something in between. We see how this influences the SLR offset. For QZSS, we played with the satellite mass, and this scales, of course, the albedo and antenna thrust effects. And I think the last one could be realistic, but our it's obvious that our box wing model is overscaled, so probably this effect is too strong here. And we can, of course, also add pulses. Here we see how much different assumptions can change the results. And if we look at the SLR residuals, then we can see red is the operational solution, and green is albedo model added, and the other 2 colors represent different antenna thrusts. So it's also difficult to clearly say that, clearly specify distinguish between IOV and FOC satellites here. For QZSS, we see how we can scale the impact by choosing a different satellite mass. We must say that there are still very big uncertainties, and I think we will have some discussions during that workshop, and afterwards we will decide which configuration we should use. But we should not forget that the orbit scale is also influenced by the antenna calibration. So if we look at the time series for one Galileo satellite, and we see in gray our operational solution, blue is the solution with albedo and antenna thrust, and also attitude model activated, and we see during eclipse seasons the residuals are larger, so the orbit is worse. And the attitude model does not improve the situation very much. There must be still something that is not modeled, for example, the thermal re-radiation of the satellites, which is not yet considered at all. Last but not least, I will tell that we did not yet forget the orbit normal mode. Also, I must confess it did not have our highest priority in the last months. So the situation was that with the normal ecom models, the orbits and then also based on that the clocks are really poor. So we tested and simulated also different different decompositions for solar radiation pressure models, and applied them to QZSS and Beidou data, and we saw that it worked fine for shorter arcs but not so good for long arcs. And the reason is that these parameters, these new radiation pressure parameters, partly depend on the beta angle, so there are variations. If we consider the beta angle, then we can also prove the orbit determination for long arc QZSS orbits. For Beidou, it's not so critical. There, an easy model, a simple model also works. Let me conclude the talk with this to-do list. Dark green means it was already implemented at the time of the last IGS workshop, and light or bright green is just implemented or on the way to be activated. Red means that we still have deficiencies here, and yellow means we are just working on it. And as I said, we merged our processing, our NGEX processing into the normal IGS routine, so we can now work in parallel on different frontiers. And I want to refer to the talks of my colleagues Stefan Scher and Arturo Filiger, who show also improvements related to the new bias implementation at Code, and also improvements in the clock solution and discussion about the antenna model.